Welcome to our comprehensive journey through the chapter on light for ICSE Class 10. Light is a fascinating topic that not only explains how we see the world but also lays the foundation for many scientific principles. In this video, we'll explore the nature of light, its properties, and its behavior in different situations. Whether you're preparing for exams or just curious about how light works, this series will guide you step by step. Let's begin by understanding what light is and why it's so essential in our daily lives and in the world of science. Light is a form of energy that enables us to see objects around us. It travels in straight lines and can move through a vacuum unlike sound. Historically, scientists debated whether light was a wave or a particle, and today we understand it exhibits both behaviors. This dual nature is key to understanding many phenomena, from rainbows to the colors we see. As we move forward, keep in mind that light's unique properties make it one of the most intriguing topics in physics. There are two main types of sources of light: natural and artificial. The sun is our primary natural source, providing daylight and enabling life on Earth. Artificial sources include bulbs, LEDs, and candles, which we use daily. Understanding the difference between these sources helps us appreciate how light is produced and controlled. Each source has its own characteristics, such as brightness and color, which affect how we use them in different situations. One of the fundamental properties of light is that it travels in straight lines, a concept known as rectilinear propagation. This explains why shadows form and why light beams don't bend around corners. You can observe this by shining a flashlight through a narrow slit or using a pinhole camera. This property is the basis for many optical instruments and helps us understand how images are formed. Reflection is the bouncing back of light when it hits a surface. This is why we see ourselves in mirrors and why shiny objects gleam. There are two types of reflection: regular and diffused. Regular reflection occurs on smooth surfaces like mirrors, producing clear images, while diffused reflection happens on rough surfaces, scattering light in many directions. Understanding reflection is crucial for studying how we see objects and how various devices work. Laws of reflection are simple yet powerful. The first law states that the incident ray, the reflected ray, and the normal all lie in the same plane. The second law says that the angle of incidence is equal to the angle of reflection. These laws apply to all types of reflection and are fundamental to understanding how mirrors and other reflective surfaces work. They also help explain everyday phenomena like seeing your face in a pond. Mirrors come in different shapes, each serving a unique purpose. Plane mirrors are flat and produce images that are the same size as the object. Concave mirrors curve inward and can focus light, making them useful in torches and shaving mirrors. Convex mirrors bulge outward and provide a wider field of view, which is why they're used in vehicles for rearview mirrors. Understanding these types helps us see how mirrors are used in daily life. When you look into a plane mirror, the image you see appears to be the same size as you and is located as far behind the mirror as you are in front of it. The image is virtual, meaning it cannot be projected onto a screen, and it is laterally inverted, which is why writing appears reversed. This simple property of plane mirrors is the basis for many optical illusions and practical applications. Spherical mirrors are sections of a sphere and come in two types: concave and convex. Concave mirrors focus light to a point, making them useful in headlights and solar cookers. Convex mirrors spread light out, providing a wide field of view. The way these mirrors form images depends on the position of the object relative to the mirror's center and focus. Let's explore how images are formed by these mirrors in detail. Principal axis is an imaginary straight line that passes through the center of curvature and the pole of a spherical mirror. The focus is the point where parallel rays of light either converge, concave, or appear to diverge from convex after reflection. These concepts are essential for understanding how images are formed by spherical mirrors and for solving related problems in your exams. Concave mirrors can form real or virtual images depending on the position of the object. When the object is far from the mirror, the image is real, inverted, and smaller. As the object moves closer, the image becomes larger. If the object is between the focus and the mirror, the image is virtual, upright, and magnified. This property is used in makeup mirrors and telescopes. Convex mirrors always produce virtual, upright, and diminished images, no matter where the object is placed. This makes them ideal for security and rearview mirrors as they allow a wider area to be seen. The images formed are always smaller than the object, which helps drivers see more of the road behind them. Spherical mirrors have a wide range of uses in our daily lives. Concave mirrors are used in headlights, shaving mirrors, and solar devices, while convex mirrors are found in vehicles and security systems. Understanding their properties helps us appreciate how these mirrors make our lives safer and more convenient. Refraction is the bending of light as it passes from one medium to another, like from air to water. This bending occurs because light travels at different speeds in different materials. Refraction explains why a straw looks bent in a glass of water and is the principle behind lenses and many optical instruments. Laws of refraction, also known as Snell's law, state that the incident ray, the refracted ray, and the normal all lie in the same plane. The ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant for a given pair of media. These laws help us calculate how much light bends when entering a new medium. Refractive index is a measure of how much light slows down in a medium compared to a vacuum. A higher refractive index means light bends more when entering that material. Glass has a higher refractive index than air, which is why lenses can focus light. This concept is crucial for understanding how optical devices like glasses and microscopes work. Total internal reflection occurs when light tries to move from a denser to a rarer medium at a certain angle, causing it to reflect entirely back into the denser medium. This phenomenon is used in optical fibers and periscopes. It's also why diamonds sparkle so brilliantly as light bounces inside before exiting. Critical angle is the minimum angle of incidence at which total internal reflection occurs. If the angle is greater than this, all the light is reflected back into the denser medium. This concept is vital for understanding how light behaves in optical fibers and why certain materials can trap light inside them. Total internal reflection has many practical uses. Optical fibers use it to transmit data over long distances with minimal loss, making high-speed internet possible. It's also used in binoculars, periscopes, and even in some medical instruments. Understanding this principle helps us see how light can be controlled and directed efficiently. Lenses are transparent objects that refract light to form images. There are two main types: convex converging and concave diverging lenses. Convex lenses bring light rays together while concave lenses spread them apart. Lenses are used in glasses, cameras, microscopes, and many other devices that help us see better or magnify objects. Convex lenses are thicker in the middle and thinner at the edges. They converge parallel rays of light to a point called the focus. These lenses are used in magnifying glasses, cameras, and the human eye. The way they bend light allows us to see small objects more clearly and focus images onto screens or film. Concave lenses are thinner in the middle and thicker at the edges. They diverge parallel rays of light, making them appear to come from a single point. These lenses are used in spectacles for correcting short-sightedness and in some optical instruments. Their unique shape helps spread out light and correct vision problems. Image formed by a lens depends on the type of lens and the position of the object. Convex lenses can form real or virtual images, while concave lenses always form virtual, upright, and diminished images. Understanding how to draw ray diagrams for lenses is essential for solving problems and understanding how devices like cameras and projectors work. The power of a lens measures its ability to converge or diverge light. It is calculated as the reciprocal of the focal length in meters. A lens with a short focal length has more power. This concept is important for understanding how glasses are prescribed and how different lenses are chosen for various applications. Lenses are everywhere in our daily lives. They help us see clearly, magnify small objects, and capture memories through cameras. From eyeglasses and microscopes to telescopes and projectors, lenses play a crucial role in science, medicine, and entertainment. Understanding their uses helps us appreciate the importance of optics in technology. Dispersion is the splitting of white light into its component colors, as seen in a rainbow. This occurs because different colors of light bend by different amounts when passing through a prism. Dispersion helps us understand the spectrum of visible light and is the reason we see colorful patterns in nature and experiments. Visible spectrum is the range of colors that the human eye can see, from red to violet. Each color corresponds to a different wavelength of light. The spectrum is revealed when white light passes through a prism, showing all the colors in order. Understanding the spectrum helps us learn about light's composition and its role in nature. Rainbows are a beautiful example of dispersion in nature. When sunlight passes through raindrops, it is refracted, reflected, and dispersed, creating a spectrum of colors in the sky. Each raindrop acts like a tiny prism, splitting the light into its component colors. This natural phenomenon is a perfect demonstration of the principles of light we've discussed. Scattering occurs when light is forced to change direction by particles in the atmosphere. This is why the sky appears blue during the day and red during sunrise and sunset. Shorter wavelengths, blue, are scattered more than longer wavelengths, red, giving the sky its characteristic colors. Scattering helps explain many natural phenomena we observe every day. Tyndall Effect is the scattering of light by particles in a colloid or in very fine suspensions. It explains why beams of sunlight become visible when passing through mist or dust. This effect is used in laboratories to distinguish between true solutions and colloids, and it's a great example of light interacting with matter. Human eye is a complex organ that uses lenses and light-sensitive cells to form images. Light enters through the cornea, passes through the lens, and is focused onto the retina. The retina converts light into electrical signals which are sent to the brain. Understanding the eye's structure helps us appreciate how we see and how vision problems can be corrected. The eye works like a camera, focusing light to form clear images. The lens changes shape to adjust focus for near or distant objects, a process called accommodation. The iris controls the amount of light entering the eye, ensuring we see well in different lighting conditions. This remarkable system allows us to experience the world in vivid detail. Common vision defects include myopia, short-sightedness, hypermetropia, long-sightedness, and presbyopia, age-related loss of focus. These defects occur when the eye cannot focus light correctly on the retina. They are usually corrected with lenses which adjust the path of light entering the eye. Understanding these defects helps us see the importance of regular eye checkups. Vision defects are corrected using lenses. Concave lenses correct myopia by diverging light rays, while convex lenses correct hypermetropia by converging light rays. Presbyopia is often corrected with bifocal lenses. These solutions help millions of people see clearly and lead active lives. Persistence of vision is the phenomenon where an image stays on the retina for a short time after the object is removed. This is why we perceive motion in movies and animations. The brain merges rapidly changing images into a continuous scene, allowing us to enjoy smooth motion in films and videos. Optical instruments use lenses and mirrors to enhance our vision or capture images. Common examples include microscopes, telescopes, cameras, and projectors. These devices rely on the principles of reflection and refraction to function. Understanding how they work helps us appreciate the role of optics in science and technology. A microscope uses a combination of lenses to magnify tiny objects, allowing us to see details invisible to the naked eye. It's an essential tool in biology and medicine, helping scientists study cells, bacteria, and other microorganisms. The microscope's design is based on the principles of refraction and magnification. Telescopes allow us to observe distant objects in space by collecting and focusing light. They use lenses or mirrors to gather light from stars and planets, making them appear closer and clearer. Telescopes have revolutionized our understanding of the universe and continue to be vital tools in astronomy. Camera captures images by focusing light onto a photosensitive surface, such as film or a digital sensor. The lens system adjusts to focus on objects at different distances, and the shutter controls the amount of light entering. Cameras are used in photography, filmmaking, and security, making them an essential part of modern life. Projectors use lenses to enlarge and display images or videos onto a screen. They work by shining a bright light through a small image and focusing it with lenses. Projectors are widely used in classrooms, theaters, and presentations, making information sharing and entertainment more engaging. A magnifying glass is a simple convex lens that makes small objects appear larger. It's used for reading fine print, examining details, and in scientific studies. The magnifying glass demonstrates the basic principle of how convex lenses converge light to magnify images. Periscope uses mirrors or prisms to allow observation from a hidden position. It's commonly used in submarines and by soldiers in trenches. The periscope's design is based on the laws of reflection and total internal reflection, making it a practical application of light principles. Fiber optics use total internal reflection to transmit light signals over long distances. These thin glass or plastic fibers are the backbone of modern communication, enabling high-speed internet and data transfer. Fiber optics demonstrate how controlling light can revolutionize technology and connectivity. Lasers produce a narrow, intense beam of light with many uses in medicine, industry, and entertainment. They work by stimulating atoms to emit light in a very controlled way. Lasers are used in surgeries, barcode scanners, and even in light shows, showcasing the power of harnessing light. We've covered the essential concepts of light as per the ICSE Class 10 syllabus. From the nature and behavior of light to its applications in daily life and technology, understanding these principles opens up a world of possibilities. Whether it's seeing a rainbow using a camera or connecting to the internet, light plays a vital role in our lives. Keep exploring and let your curiosity about light guide your learning journey.